site or distance variable.
Good afternoon. Our UTDesign project involved working with Kasling aircraft to design a system that measures distances based on radio waves, which would be then integrated into systems on board unmanned aerial vehicles. I'd like to introduce the team. Brian Differ worked on component research, PCB layout design, and assembly. Stephen Prophet, who worked on our power receive method, coding, and as well as the RF counter coding. And Austin Eve, who also worked on RF counter coding, helped with the RSSI coding. My name is James Stratton. I worked on some of our initial calculations, PCB layout, assembly, and component research. Upon completion of this device, Kasling aircraft would incorporate it in order to send distance data to the state estimator on board the UAV. This would give the UAV the ability to make in-flight corrections to avoid collisions in the case of GPS loss. In the beginning, we started our research by finding other designs that used radio waves to measure distance. We narrowed our research down to two basic theories. One was a counter method, which would count the time it took for a radio signal to be sent, received by another device, and then sent back. The other was power received, which we would measure the power received and then develop a reference in order to determine distance. For the power received, we looked into the received signal strength indicator, finding a prototype on board that gave us access to this RSSI line voltage. We used a microcontroller and an analog digital converter to sample the analog voltage and then measure that voltage at several distances. After several tests, the best data we came up with that was at 3.25 volts. The devices would be about 50 feet apart, plus or minus 10 dB. In the end, we determined that this was not a very accurate way or reliable way to measure distances due to the multiple factors involved in measuring power received. For the counter method, we decided to go with two versions, one a lower frequency and one a higher frequency. And then we ended up building several iterations of both a 100 megahertz board and a 600 megahertz board. In the end, the 600 megahertz board didn't work, and we believe that was due to the RF issues associated with the 600 megahertz clock signal. The 100 megahertz board did work, and we tested it using software that simulated the time it took for the signal propagation delay. During those tests, the counts that were provided were very nearly the counts that we got when we were doing our initial calculations prior to building the board. Those minor differences were consistent and could be easily dealt with in future implementation. The trouble came though when we used our we took out the code and we used the actual transceiver. The devices communicated correctly. However, that transceiver had such a great delay in it that the counts that we got correlated to thousands of meters, even though they were only just a few meters apart. And so at this time, we would recommend to Kasling aircraft do not use a low power transceiver because it goes into a standby mode when switching between transmit and receive or vice versa. We would even go further and say do not use a transceiver at all, so that instead use a dedicated transmitter and a dedicated receiver so that we could actually detect the incoming signal on the receiver as soon as possible in order to stop the counters as soon as possible and then to have an accurate distance. At this time, we'd be glad to answer any questions.
Could you talk a little bit about your initial charge from Kasling aircraft? What did they want you to do?
Well, initially, Kasling aircraft was very general about what he wanted, Trey Kasling. He wanted something that would be under a pound so that it would work on the unmanned aerial vehicles. He wanted us to use as many off-the-shelf components as possible. And that's one of the reasons why we stuck with our transceiver that we got in Senior UTDesign 1, because it was an off-the-shelf component and it worked well with the Arduino that we use. We chose Arduino because that's what he uses on his aircraft at the moment. I think we would have gone with a much faster processor if we weren't, focused in on trying to implement it on the systems he already had.
Given the power constraints of how much power was sent?
We asked that several times. The board that we actually uses at max would use half an amp, and so we were worried about that. But actually, the batteries that they use on their aircraft provide up to 40 amps at 11.7 volts. 600 megahertz board and the 100 megahertz board had 4 of those counters. So we ended up with a 16-bit binary number, which we use to translate into a count, and then use that based on the frequency determinants.
One factor with that as we, one thing that was stated in the first semester is our total count number. We addressed at that point that it was an 8-bit, and recommendations were to improve that count bit. But if we go beyond 16 bits, we start dropping our frequency down. So using our low speed method, we have a 4-bit binary counter. So with the propagation delays, we're trying to control that 16-bit count. We dropped up, our maximum frequency was 100 hertz, or 100 megahertz. And if using our high speed, when we were trying to design for the 600 megahertz, or initially designed for 900 megahertz, when you try to include up to 16 bits, it drops us down to 625, just due to the propagation delay trying to control the signal.
What was the accuracy requirement that you needed to meet to make this successful? And how accurate did it have to be? And what was the distance?
Right. Originally, he asked for 2 feet, and so that's where we came up with our 600 megahertz frequency. Theoretically, 600 megahertz, we get 1 count, and it would be within half a meter. And again, our first semester, we focused really hard on the counter method, and actually designed a few microstrips to account for the RF issues for the transmission line. We had a problem. We had to taper those transmission lines in order to connect to the pins on those chips, and so we created reflection, and it ruined our impedance matching. And so what we tried to do was put all the devices close together as possible, within 10% of that wavelength, in order to get rid of those issues. But it didn't end up working, so that's why we made 2 frequencies, so that we could have a frequency that we knew would work, that would prove our theory, and it would have a 3-meter accuracy, which actually worked for some of the unmanned aerial vehicles that, instead of quadcopters, he has some planes, and those wingspans, 7 feet long, 3 meters would actually be a good distance for them not to come within each other.
I'd like to make one addition to that. In the first semester, we actually tried to create our own clock signal, working with the clock, with the counters that we found. At the frequencies we were desiring, there was only 1 or 2 counters that really we could find that were available. So the first semester, we tried to design our own clock. That wasn't successful. Caveat to that was we did not have an O-scope that could allow us to see the frequencies at 600 or greater. We were limited to 300. So at the beginning of the second semester, we actually came up, found a clock generator that worked and had compatibility issues, the voltage levels with our counter. And so that made things a lot easier. It's actually programmable. We can program it from 50 to 800 megahertz. So we're actually using the same counter on both the times. So there should be a better integration in the future.
If I could just ask, is the purpose of this for each unmanned vehicle to be able to know where the other unmanned vehicle is? Is it for on view? We have multiple vehicles following each other?
What was it
That
like?
was one of the
I can think of it like you're doing aerial reconnaissance to see monitoring the border. You might have many of these unmanned vehicles flying information surrounding the
One of Kasling's goals going into this was, and he reiterated this quite a few times, was he wanted the aircraft to be able to fly in a formation without colliding with each other. A lot of this was to account for the slight drift of their courses, so they wouldn't end up crashing each other. They could readjust once they determined they were too close together.
So it's mostly for between the vehicles
Correct.
themselves, it's not to the ground.
Correct. And this is to supplement the GPS. This isn't to be a main
Or
device.
in absence of.
Right. If the GPS goes down, he wants to be able to make sure they don't crash into each other, and he can get them to land, fix whatever's going on, replace the GPS module, and get them back in the air.
Other questions?
Do you do any testing at frequencies different than 100 megahertz to simulate Doppler? Is it going to interfere with your signal strength?
No. I mean, we tried to use the 600 megahertz board again, but the clock signal at 600 megahertz, we had a hard time trying to get that to propagate to the counters. The transceiver we